All right, so we're going to get going. Need to do a little bit of housekeeping before we get going and turn it over to Ryan. Need to thank all of our sponsors. You can see them on the screen here. They're the ones that are helping us to keep this at a no-cost event, helping us to pay the freight for this web platform. So we want to thank all of our great sponsors, including the APWA Colorado CARS and the Federal Highway Administration's our partners. And BG Chemical Company, Black Magic and Benvix Technologies are their companies. Our paving contractor, Schmidt Construction and Colorado Asphalt Services. Our maintenance contractors, Foothills Paving, Vance Brothers, and A1 Chip Seal. We want to thank all of them for their effort in helping us to keep these at no cost. While the webinar is going on today, if you do have questions, you can, if you have the ability to unmute yourself, go ahead and do so. If you don't have that ability, you can use the chat window. You can find that at the bottom of the screen. On my screen, it's on the right-hand side. There's a little chat call-out button there. Go ahead and use that chat window. If you have a question, I will interrupt Ryan and ask the question, or if it can wait, I will make note of those questions and we'll come back to Ryan at the end. So Ryan, I'm going to go ahead and turn it over to you. You can go ahead and introduce yourself and give everybody your background. And thanks for being here.
Appreciate it, Tom. Thanks for having me. My name is Ryan Proctor. I am the technical manager for Suncor Energy, and I am having issues with my computer, of course. Bear with me here a second. I'm the technical manager for Suncor Energy. I've worked with hot mix asphalt, concrete, aggregates. I've been on paving jobs, pavement preservation jobs, recycling jobs. So I've kind of done a little bit of everything for the last 20 years. And my goal today is to talk to you guys and give you an understanding of how an asphalt producer looks at performance grade binders, how they're selected, and their best uses. So with that being said, I understand how this works. I like virtual meetings in some sense because it's easy, right? We can all get together and watch a presentation, and I appreciate Kappa for hosting this, but I know that if you're not engaged, sometimes the presentations miss some impact. So I encourage everybody, if you have a question, even if it's not 100% related to what I'm talking about, my goal here is really to educate you. And if I can help with any of your questions, I'm more than happy to do that. So let's get started. Asphalt roads, why are they important? First of all, they're important because they're everywhere. Everybody drives on asphalt roads. They make up about 92 to 95% of the roads in the United States. I've seen some different stats there, so that's why I put the range in there. But one of the key points about asphalt, and I'm thinking about Colorado specifically now, is we need an asphalt binder that'll work in the situation on the picture on the left with heavy traffic, slow moving, heavy trucks, and we need an asphalt binder that'll work on the situation on the right. You know, colder climate, still a lot of truck traffic, potentially a lot of freeze thaw cycles. So I'm going to talk about what we do in the industry and what the specifications look like so that you get a binder. In some cases, you might get a binder that'll work in both situations, but I'll discuss that. So before I talk about where we're at with PG binders, I really think it's important to understand where we came from. I won't spend a lot of time on these slides unless there are questions, but this is the beginning. There are naturally occurring asphalts in the world. There are some that are still being used for pavement. They have some benefits. They have some different physical properties than some of the binders that we make at refineries, but there's some downside to it. A lot of the asphalt binders, if you look at that little, I guess that would be an asphalt pond maybe. Just kidding, but there's fillers in there, solids that get put in there. You don't have a lot of control over what you get. You get what you get, and then there's logistical issues. We don't have anything like that in Colorado. There have been trials of projects like that in Colorado and around the West, but nothing recent. And shipping those materials in can be problematic and expensive. So going back to the old days of asphalt paving, I would just summarize it as you got what you got. There wasn't a lot of control. There wasn't a lot of testing. You got asphalt. So that's what we started with. So the first step along the road to really getting control of what we're putting in place is a penetrometer. This isn't something that's used a lot in asphalt grades anymore. We do still use it in emulsions. I'm not going to speak on those unless people have questions. But the goal of the penetrometer, if you look on that picture maybe in the upper left, is you have a pin tin that has asphalt in it. And in the old days, they could store that asphalt at a variety of different temperatures. And you dropped the needle, which was a modified sewing needle, into the pin tin, and you measured how deep of a deflection you could get when the needle was dropped into the pin tin. There's also a weight, and the apparatus itself had weight. And for the most part, you dropped it for about 5 seconds, but again, there are varying specifications. So the good thing was, if you go back a slide, right, compared to this, we're starting to get a little bit of control now. We can understand how soft our asphalt is at room temperature. We've come a long way from then, but that's really the first step in the process. Another thing that I would like to mention before I move on, and at Suncor, we have a refinery in Commerce City here. I don't think this is the way we look at it. So I have simplified a refinery down about as simplified as I can get. This is not actually what it looks like though out in the field. We bring in crude oil and we use something, multiple distillation units. Sometimes they have pressure, sometimes they have vacuum. They all use heat, and they separate all of the different components in crude oil. So the lightest material might come off the top. Methane, propane, for example, they're really short molecules. And then if you take off everything else that we can sell, gasoline, diesel, gas oil, there's a lot of other grades in there that I didn't put. What you're left with is asphalt. So if you go back to this slide, if you wanted something a little bit lighter, you might not pull out as much gas oil. If you wanted something a little heavier, you might pull out a little bit of gas oil, a little extra. And there is gas oil that still exists inside the asphalt. It is part of what makes it soft and pliable. So now we're moving forward a little bit. Along with early refined asphalt, where we had more control over what we were supplying, they had more control in the field with what they were paving. And I'm not going to focus on that. That's not my point here, but you can see that we're making incremental steps towards better asphalt pavements. The next step, we have to skip ahead quite a bit here. All of these tests take some time to develop. So even though it was adopted in 1963, this test had been around longer than that. And there were some agencies that used it even before 63. But this asphalt viscometer, it might be hard to see that tube on the bottom with the white background. But you use a first of all, you put the sample in a bath, you look on the right there, and you can run a viscosity at a variety of different temperatures. Typically, we would run these at 140 degrees Fahrenheit, or we would run them a similar viscosity at 275 degrees Fahrenheit. And you use a vacuum to start the asphalt going, and you measure the time that it takes to go in between two marks on a vis tube, and you run it a couple of times on the same vis tube and take the average. And the thought on this test is that the lighter, the less viscous the material is, the faster it flows through the tube, the heavier it is, the longer it takes. So at this point, we had a few other specifications. I'll mention Flashpoint and some of that later, but from a performance standpoint, it was predominantly viscosity and penetration, and we ended up with issues on the roads, right? Because if you look at road performance, how we do at 140 degrees and how we do at room temperature is somewhat important, but it doesn't tell the whole story. So we saw a lot of roads that look like this. And one other thing I should mention, obviously the asphalt binder isn't the only cause or potential cause of some of these issues, but at the time we felt like new specifications would help improve the binder and would help improve their performance, which would help reduce these problems. So rutting was a big issue. cracking and alligator cracking, and I'll talk about those with the newer tests here in a minute. So anyway, that gives you some background. That's how we got to where we are now. For the rest of the presentation, I'm gonna focus on the PG grading system. I'm also going to talk about some of the tests that aren't part of the PG grading system that the Colorado DOT and other agencies still use across the country. Talk about binder tests, specifications, how we select binders, and then talk about their use. So just to kind of hit this home one more time, if you look at that can on the left, if you took asphalt, normal asphalt, I should say, something that wasn't really hard, something you would pave with, and tilted it on its side, eventually that asphalt would creep out of the can and onto the ground. Asphalt has some interesting properties where it's liquid in some cases, it's a viscoelastic material. It's liquid in some cases and it's solid in others. So with this asphalt, if you heat it up to 100 degrees, in an hour, it's going to flow pretty quickly. At 30 degrees, it's going to flow, but it's going to take longer. That's probably fairly intuitive. Different asphalts are affected differently, though. You could take the same asphalt that meets the same specification when we're talking about the old system, and it might take you 2 hours to do that. So what tests could we put in place to make sure that the asphalt binders we were using would perform in the field at the temperatures and at the truck loading levels and traffic loading levels that we needed to? This is an old asphalt slide. I took this from Marshall Shackelford. This is from the 50s, actually. And it shows again that if you're looking at T1, so the bottom part of that graph is temperature. And if you will, those lines are the performance of an asphalt. So it's simplified, right? And if you look at both of those asphalts at T1 at the temperature, whether it's penetration or viscosity, they could look the same. But if you look at them in the road, or if you looked at them in the lab under different conditions, they have very different performance. And this slide really focuses on how temperature susceptible different asphalts are. So that brings us to PG binder testing. There was a significant amount of work from the FHWA, the Asphalt Institute, paving associations, contractor. I mean, our whole industry was really involved in this effort in the late 90s, and it was to get the performance-related tests back into the system. So if you look on the bottom of that slide, right above pavement temperature, you'll see that we're looking at tests that cover. And minus 12 is just an example. We could look at tests that cover the range from minus 30 degrees or minus 36 degrees Celsius up to tests that are even higher than 135 degrees Celsius. And the goal is to find out how the binder will perform at those different stages. So at the colder tests, we're looking at cracking. And I'll talk about this later, but that beam, we're trying to get to crack in the lab. In the two middle tests are a DSR, dynamic shear rheometer. And in that test, and I'll focus on this later, you're looking at the performance maybe under road operating conditions with fatigue of the road over time and with rutting potential. And then as these new tests and new criteria were put in place, people were having issues making binders that had so much polymer in them that they couldn't pump them. So that last test on the right is really just to make sure that a hot mix plant can pump the material as they use it. These tests are similar. There's a safety aspect to our testing as well. Flashpoint is something that is run at the refinery, even on the gasoline that you use in your car if you have a gas-powered vehicle. In that flashpoint, we heat up that asphalt in this case until you can take a flame and brush it over the surface of the cup, and it gives you a flash. And the goal there is that we would not want to give a paving contractor something with a low flash that they could have safety issues with their plant or smoking issues, out with the community. Another key point here with this testing is that it was very, I think empirical might be the right word. It was very deliberate on how we looked at these tests, that we wanted something to simulate every aspect of what the binder would see in the field. Prior to a rolling thin film oven, there was a thin film oven, and I don't have a picture of that here, but work was done to show that it didn't really age the binder the way that a hot mix plant would. So if you opened up a rolling thin film oven and you look on the right there, there's a fan, and that carriage spins kind of like a revolver. So it's spinning like a clock with the picture that we have there. And then there's an air nozzle that's blowing air into those tubes. And the whole point of this is to simulate the hot mix plant. And there's been some work to fine tune this, but the goal here is you put the binder through this oven and you can test it afterwards, and that'll give you an idea of what the binder will look like after it's been through the hot mix plant. Another step, I should mention too, on both of these tests, actually, your test may not be the right word, but you're not getting a value. These are just conditioning steps in the process. So the pressure aging vessel is similar. You put the asphalt on a pan on the left, and those PAV pans are very similar and in most cases identical to the old thin film oven pans. Those pans go into the pan holder, which is on top of the machine, and you can put several pans in there, and then they slide down into that pressure aging vessel. The goal of that apparatus is to simulate what the asphalt binder looks like when it's been on the road. I don't want to talk about time frames because there's been a lot of work that has different conclusions on how much time this really simulates in the road. But the goal here is to simulate what happens in the road. And another point to mention is that this oven was set up so that if you were specifying something in cold weather in Canada, you wouldn't heat it as hot as if you were putting down asphalt in Death Valley in California. So this test takes about an hour and a half, roughly. There's some steps you need to do with the samples before you put them in and after. And this takes about a day after everything's done. This is the flash point. I mentioned this earlier. This is more for safety than anything else. We've used this in the industry for long periods of time, well over 50 years. And again, the goal is to figure out at what temperature the asphalt can be heated to where you would get a flash or a flame over it. One of the things that this also helps protect against is everyone at some point or other around the country has had somebody approach them about putting other materials into asphalt. And we would not want, as an industry, we would not want to put anything in asphalt that would put anybody at risk. Rotational viscosity, I mentioned earlier. There's a cup. If you look in that top slide there, you can't really see it, but where that person's holding the spindle, underneath that is a reservoir of asphalt. And that spindle that is being held is similar to what those spindles look like in the bottom. They're twisted. It's hard for me to show virtually here, but twisted like this continuously. And you're measuring the resistance to that force. So the more viscous the asphalt is, the slower and the more resistance you get when you spin it. And again, the original point of this was for pumpability. Needed to make sure that these new polymer systems that were being used could work in a hot mix plant. But another thing that we use this for is a temp vis curve. And I can talk about that later if somebody wants to know more about it. But the goal behind that is that an hot mix asphalt plant and a hot mix asphalt mix designer would know what temperature to mix the asphalt binder at. And then in the field, there are a lot of factors that affect it. So it's not by itself the exact guide to what you need to compact it at, but it's a good starting point on the temperature where you can start to get compaction with that binder. So this is rutting. One thing you'll notice, and for everyone who's been through an asphalt class, I think all of us try to collect the worst case scenarios that we can. I have a worst case in this, but it wasn't feasible. You can see from that phone that it's a pretty old picture, right? We don't have phones like that anymore, but this is what we're trying to avoid. So this is the DSR. It kind of looks like a UFO in my picture, but if you look at the top left picture, it's a flat plate with a spindle on top of it, and it's oscillating back and forth. The rotational viscometer spun around continuously. This oscillates back and forth, and it makes very small movements. So if you look on the top, I have a point B, A, and C. And then if you look at the graph there, it goes, you know, if you're looking straight at what you would see in the test, that plate would oscillate to where you would look at A, then B, then A, then C, then A. And that gives you an idea what the oscillation looks like. The lower plate is fixed. So what happens is if you have an asphalt binder sample on top of that, I mentioned that it works somewhat like a solid, somewhat like a liquid. The reaction time will be different than when you put the force on there. So this is what a DSR looks like. The machine is putting a stress onto the sample, and the strain is the reaction that you're measuring. And I've oversimplified this. Again, if somebody has comments or questions, we can talk about this further. So in an elastic sample, let me just skip here. You can see that when something is viscous, when something's viscous, this is kind of my definition. It's very thick. It's the honey or molasses part of it, or peanut butter even, that resists change. It's more of a solid. When it's elastic, it's different than not being viscous. An elastic material has a lot of stretch to it, where you could stretch it and expand and contract it. It'll have a different reaction. All right, let's talk about thermal cracking. This road was not in Colorado, I should say that ahead of time. But this is one of the worst roads that I've seen. And you can't really tell there in that picture, but the crack sealer, they had crack sealer and they had even gone in and tried to pave that crack. And those crack sealers and paving, I don't know what you call them, patches, it also cracked all the way through. So how do you avoid something like this? Well, the first thing I'd say is you have to understand what the asphalt binder's role is in the material. When the pavement temperature changes, the asphalt needs to be able to expand and contract, because what happens is as the temperatures cool down, it doesn't matter what the substance is, they all do it to different degrees, but the asphalt binder is going to contract, right? It's going to get cooler. And if you don't have a way to relieve that, you end up with a crack. So all of the pressure from this asphalt road was focused on that point, and it cracked.
Ryan,
go ahead.
I've seen cracks like that in Colorado Springs. just in case anybody's interested, they do happen in Colorado like that.
I just didn't want to anyone think I was bad mouthing our roads, but you were right. This road was so bad that the trucks, this is not a joke either, the trucks were going 40 or 50 miles around a specific road because they didn't want to have issues with their brakes and shocks. And those cracks were every, I don't know, 10 to 15 feet for 10 miles. So the bending beam rheometer, the goal of this test is to look at the asphalt and see how it's going to perform in cold temperatures. So if you look at that black bar, that's an asphalt beam. You make a very small mold. Let me see if it's in here. You make a very small mold. You can see it there. You pour the asphalt into it. You let it cool down and harden, put it in a freezer, and you scrape off all of the asphalt that's overflowing, and you pull off all of those pieces, and you end up with a beam like that. That's very solid. That material gets put into a bath. I'll talk about the PG grades here in a minute, and this is another one I can explain more on if people have questions, but we're putting these samples in 10 degrees warmer than what the specification calls for, and that all has to do with the timing of the test. It's very complicated. So this material, I kind of think about it like a stick. You know, if you see your kids trying to snap a stick in half, it's similar, except instead of using the force on the ends like I'm doing, we're holding those ends in place, and then there's a rod that comes down and pushes it, and it starts to deflect it, and at some point it'll snap it. So I talked about the mold. This is another stiffness plot, and I think there's two things to really remember here without getting into all the details here. We're looking at the stiffness over time as we're bending that sample, and at 60 seconds, so at 1 minute, the slope of that line is the M value, if anyone has seen the M value in a test. And I don't know, 99% of the time, the M value is a minimum of 0.3 at whatever the testing temperature is that you're looking at. And then the stiffness is usually 300 megapascal maximum. All right, last set of issues here. Fatigue cracking. This is one of the harder ones to troubleshoot, and I think our thoughts were really in the right place as an industry, but the test I'm going to talk about hasn't completely fixed this issue, obviously. So I mentioned asphalt's elastic. I view asphalt in this respect like a paperclip. You can bend that asphalt back and forth so many times, and at some point that paperclip loses its elasticity and snaps. And that's very similar to what happens in the road. So as this hot mix road has been down on the road, it's oxidized. Some of those light ends, some of those gas oils start slowly coming out over time. This road doesn't look as old as some of them that you'll see that have fatigue cracking. This could have even been a base issue potentially, but you'll start to see some of these spider web cracking. So the test to try to prevent that is another DSR. This DSR we were running after the PAV. So let me back up before I go on to the PAV DSR and tell you that with the DSR, there's really three different times that we're looking at it in a pavement's life. We look at an original DSR, so what that material looks like when it's being shipped or stored, either by the refinery or the hot mix plant. Then we look at it after the RTFO test. We want to see what that binder is going to look like before it's being put down on the road or as it's being put down on the road. And then finally, after the PAV test. So this test is to try to simulate what that binder will look like after it's been on the road for a different amount of time. And instead of having a minimum value, most of the other DSRs, you want a minimum value because you want that material to be strong enough to resist rutting and to resist some of those high temperature forces. In this case, you want it to be, weak isn't the right word, but you want it to be flexible enough that and elastic enough that it doesn't go over 5,000 megapascals. And the thought at the time was, if it goes over 5,000 megapascals, you're more likely to see this. So I will tell you that there's a lot of research being done on this specific aspect of binder testing. We're not as confident about this as we used to be. There are also binders, and this doesn't really affect people in Colorado, but there are binders in other places based on the crudes that they use that they are over 5,000 all the time and people don't see issues. But it's still a specification, something we don't have an issue with. The mix, obviously, and how long the mix has been down also play a big part in this issue. All right, I went through this all fairly quickly. I mentioned everything except for one test that's on here. If I go back, I'm not going to go back. If I go back to that RTFO graph and you think about that carriage that's rotating, we can take an asphalt binder, and it's kind of like running a moisture value on an aggregate or a hot mix sample. We'll weigh the asphalt before we put it in the RTFO, and we'll weigh it after we put it in the RTFO. And the goal of that test is that we don't want there to be a lot of light ends or material that gets burned off in the hot mix plant. When that happens, you're more likely to see smoking issues or odor issues, and it could even be a safety issue. The loss on heating test and the flash point, I would say for the large majority of the time, the vast majority of the time, have eliminated those issues. But it is important that those tests stay on a specification. All right, SHRP plus tests. I'm not going to go all the way to the beginning of my presentation, but I did skip some things. When I talked about penetration and absolute viscosity, I even mentioned thin film oven. What happened is before the super pave effort to put in all of these specifications, people came up with their own systems to measure some of the same things. So these SHRP plus tests, and I'll talk about a few of them, there's actually quite a bit of them, are older tests generally that look at performance in a different way. And why they usually still exist, and Colorado is a good example of this. Before CDOT had 6428, they had AC20P and AC20R. I should say that really covers our whole region. When they went to PG 6428, they still liked some of the performance they were getting from these tests, and they left them in place. And if you look across the country, that's usually what you'll see is people like the performance that these SHRP plus specs gave them. So what they might do is specify, like in CDOT's case, a 6428, and then add some of these other tests. This is one of the tests that you'll see in Colorado. I'm really going to talk about two tests here. They're similar in some sense. You look at that mold in the top. That's you put asphalt kind of into a dumbbell shape. Different specs have different sides, but they're all somewhat similar. And then they go into a ductility bath. Generally speaking, those ductility baths are either at room temperature or at 4 degrees Celsius. And for a ductility, they pull these out slowly until they break. And when those break, that's the value that you get. So the more elastic polymer and binder you use, the longer those tests go for. With the ductility, you cut the test either at 10 or 20 centimeters, and you measure those little, I don't know what I would call them, those little ends pieces, and over time they shrink back. And again, the more elastic the material is, the more elastic recovery you'll get. So I would say if you look at the country, you will see elastic recovery used a lot more than ductility. But if you looked at our region in the United States, it's really the opposite. And it's a lot of the states that were using the old AC20P or AC20R specs, and they liked the performance they were getting, like CDOT. This is a toughness and tenacity spec. One of the first toughness and tenacity machines in existence was housed at the Commerce City Blue Knight plant. When Coke had it, when Conoco had it, going back in time, that test was really developed here and in this region of the United States, and is still used by CDOT today. So in this test, you take a pin tin, you put some asphalt in the bottom, and you pull the material out, and you end up with a graph like what you see on the right there. And there's two measures that you're trying to find. The toughness is at highest point, and that's when you get the most force, not the highest movement on the material, but the most amount of force. And then the tenacity is the area under the curve if you take out that initial peak. Again, it's a complicated test. A lot of people still like. If anyone has specific questions on it, we can talk about it later. But this is another test where you're kind of trying to balance two things. You want to have enough stiffness and toughness in your binder that it can resist the force, but you want enough pull or give that you can get that tenacity. And we could use polymers. We wouldn't supply these to the DOT or anybody in Colorado, but you could use polymers that give you one component and not the other very easily. And if that happens, you might be able to pull this sample up to the point that you see on the left, and it would break right there. And those aren't binders that CDOT wants in their roads. All right, hopefully I got through the part of this that's the most technical. I apologize for that, but I think it's important to understand the tests, why they're in place, and what we're trying to prevent, so that now we can talk about what that means for grade selection. Similar to the testing portion of the new set of PG specifications, and I need to stop saying new, it's been over 20 years, but the goal here was to make sure that you could look at wherever your location was, figure out the traffic, figure out the climate, and pick a binder that would meet that need. So along those lines, these are the weather stations that we have. They change a little bit over time. This is an old slide, but in general, if you have a road and you're looking at a project, you can find the weather for it. Another example here, obviously you can see the date's a little old here, but when you go in and look at these weather stations, you can find out what the temperatures look like. When you look at rutting, there's a couple of things that cause rutting. I'll talk about traffic in a minute. But the other thing are the really, really hot days, right? If it's 30 degrees outside, you're not going to see a lot of rutting unless you really have an issue with the binder or a big truck or an issue with your base or something else. But I'm focusing on the binder component of this. So you can look at this graph, see what your high temperature is, find out the elevation. You can also look at and see what the low temperature is. When you see cracking in a road, for the most part, you're seeing it on the coldest days of the year. So the old rule of thumb used to be the 7-day hottest pavement temperature. I think I mentioned that later, and the coldest day of the year. And that gives you an idea what your weather constraints are. The other thing to mention is there's been a lot of work to update the weather station data and the software that tracks this for the roads. And now we're a little more specific on the depth of the pavement, right? So we care what ambient temperature is, but if you're a designer, you probably care more about the temperatures that you're going to see in the pavement. So these are some ideas on high temperature reliability. Again, this is an older slide and it's changed a little bit. If you look down on the right, I don't know how well you can see that, but for Colorado, we're generally talking 58, 64 for the most part on the high temperature. On the low temperature, same theory here. For the most part, we're looking at minus 28, some minus 34. And again, just to note this again, these are degrees Celsius for both of them, not degrees Fahrenheit. Oops. All right, I mentioned this earlier. There's two other things to factor in though. There's a traffic adjustment portion that you can factor in. An easel is an equivalent single axle load. To oversimplify this, it really just, you want to make sure that you're accounting for trucks traffic in the way that you should in this equation, because trucks do significantly more damage to a road than cars do for the most part. So using this modification, you can figure out what the traffic's going to be. I'll talk about that adjustment though in a second. Before I get there, if you take everything that I just told you, you can kind of sum it up into these next couple of slides. So PG grading or performance grading is how we classify a binder. In this example, well, in every example, the first number is degrees Celsius, and it's derived from the 7-day average maximum temperature of the pavement, because that's generally when you're going to see you're going to see issues. I mean, the fatigue cracking is more of a long-term effect, but if you're going to see rutting, it's generally in that time frame. The second number is in negative degrees Celsius. It's not a dash, it's a negative value, and it comes from the lowest single temperature of the pavement. When I talked about those DSR tests, I skipped over the temperatures. When I talked about the BBR test, I skipped over the temperatures. You run those DSRs for this binder, you would run them at 64 degrees Celsius. And for the BBR, as I mentioned, it's complicated, but you would run it at negative 18 Celsius. And then both of these numbers are adjusted in 6-degree increments. So I'll give you an example. I don't have it in here. If you looked at your weather temperature, you looked at traffic, you might find out you needed a 61 minus 24. Well, people don't supply 61 minus 24s. If we did that, we would have to have significantly more tankage at these terminals, at the hot mix terminal or hot mix plant and at the asphalt terminal. You round up and you end up with a 64 minus 28. Another thing to mention before I talk about some modifiers is effective temperature range. So again, there's more to a pavement's performance than the binder, but what we are saying is that the binder in this case should perform in the temperature ranges of 64 to negative 22 degrees Celsius. And the range for that binder is 86 degrees. So an easy rule of thumb, if you want to determine if a binder is modified or not, is if it's under about 92 degrees Celsius, it's usually unmodified. If it's over that, it's a modified grade. So 6428, if you take the difference between them, right, we're at 92, it's a modified grade. 6422 is not. All right, polymers. Polymers, when we first started using SuperPave, polymers got a lot of attention. Then for a long period of time, people didn't seem to focus on what polymers were being used anymore. And I would say in the last, I don't know, 5 to 10 years, polymers are a big focus again, but it's more about the sustainable recycled material type of polymers. So I'm going to try to talk about both of them. Polymers are a tough subject because they're very specific. You can take a polymer with one asphalt and have it work great. And then you could take that same polymer and I could send it to a refinery or a terminal in Florida, and that might not work at all. So they're very asphalt specific. They're used in emulsions, and what they really do is they provide a lot of strength and elasticity to the binder. Not sure why I put that chemical in here, but just to give you an idea, they're very complicated. We use a couple of different polymer types for the most part. I'm not going to talk, the sustainable recycled materials don't really fit into this category, but we use linear polymers and radial polymers. And those radial polymers can look like spokes. You know, they're more three-dimensional, and they give you more viscosity, more toughness because they really bind up that asphalt. I could have a presentation just on polymers. So if somebody has questions on this aspect of it, let me know when we're done. So other modifiers. It's hard to answer a blanket statement about anything, but obviously, as I mentioned before, there are all kinds of other modifiers that are out there. There's rubber modified asphalt. You'll see that predominantly in Arizona and California, although a variety of states have looked at it at one point or another. Polyphosphoric acid, which is prohibited for use by CDOT, but there is an acid that can be used that doesn't work quite like a polymer, but it increases the asphalt's resistance to rutting. Alkali modification isn't something that I know of that people have used in decades, but that's another thing that's prohibited. And you could take a base or a caustic and do something similar to a polyphosphoric acid. When people used to do that, they used to have issues though with storage tanks or trucks because some of these materials can get corrosive. And then the one that used to make the big headlines in the last couple of years was re-refined engine oil bottoms. And there are companies out there that take recycled motor oil, and they do more than just clean it, but they'll put their own package and their own additives in there. And then some people have used that with asphalt binders. So that's not something that's typically used in Colorado. I don't think it's something that's been used in Colorado for a long period of time. There are no plans to use it, but it's got a bad name maybe out there, and I just wanted to explain it. One other thing I want to explain is that there are a lot of recycled materials that are making a kind of a comeback, and some of these materials are a little different than they used to be. Rubber is one of them. Shingles are another one. Wrap. Wrap and shingles, there's a lot of extensive hot mix information out there about them. I'm not going to spend any time on them, but with some of the just strictly polymers, people come to us all the time with that. And I'm sure they come to all of the engineering firms and all of the agencies as well. And my point isn't to say one's great or one's bad. I just think you need to be careful if you're going to try something new, that you still have a mechanism in place to make sure that you get the performance that you're used to, or maybe something better. We can talk about that at the end if people want. So here's some CDOT binder grades. if you think about my rule at 92, you can see which ones are modified and which ones aren't. 58, 28, 64, 22 are unmodified. They're used a lot in municipalities that aren't strictly for CDOT. They're cheaper. Not going to spend any time talking about costs, but you can imagine polymers add some significant cost to a binder. And then the polymer modifieds on the right, you might want to use a 58 minus 34 in a colder climate. 76, 28 might be your, I-25 mix that you're looking for to resist rutting. And again, this comes up a lot. I'm dealing with this in another state right now where people want to add another 2 or 3 grades to this mix. And that, that's always possible, but storage becomes an issue with the hot mix plant or the refinery. All right, we're nearing the end. You can tell this is an old slide. This is an iPhone 11 slide from when I think I had an iPhone 4. But my point is that even though asphalt probably seems like something people don't spend a lot of time focusing on, we're always looking for a couple of different things. We're always looking for better performance. We're always looking for cheaper options, just like everybody else is. So this test is going to be a challenge without getting technical. If somebody wants to talk about massacre or creep recovery, I think we're going to have to talk about it afterwards. I just want to bring it up because this is one of the new trends out in the industry. This test takes a look at different stress loadings, and you kind of look at it like an elastic recovery. So somebody on here knows this test, they probably think I'm crazy. But what you do is if you think back to that DSR, right, where that spindle's rotating on the top, you put a stress on it, you let it relax. You put a stress on it, you let it relax. And you're measuring how much it's relaxing. So if you had a really, really elastic polymer or binder, it's going to relax a lot further than if you have something rigid. So that's what the test looks like. You can see where you add the stress, that it goes up, and when it relaxes, it goes back down. We also look at peak strain, and that's the highest value that you get, kind of like a toughness from that toughness and tenacity test. So this test uses existing equipment, which is good, and you try to combine some of the facets of some of those SHRP plus specs. There was a movement for a while to replace some of the DSR tests with this. And in fact, if you look at AASHTO, there's a new table that specifies PG grades using just this test. A good example of that is the state of Nebraska. Nebraska uses this all the time, and they have a very different binder grading system than what we have in Colorado. All right. This is the time where I try not to, but I end up getting on my soapbox, so I apologize. First of all, I think it's important, and what I'd like you to get out of this is the binder tests are very methodical, and the goal is to predict performance. And we've come a long way in a relatively short amount of time. This PowerPoint would be outdated in a couple of years because right after Massacre, we'll have something else that we come out with to try to get even better performance. The asphalt binder specs are based on the climate and traffic. It's very important to understand that. I would also add to that there's a reason we do them in 6-degree increments, and that's because it's not really feasible to have a hot mix plant with 8 tanks for binder if it's a small plant, or a specialty plant that might have 16 different tanks in place. It's always nice to think about other binder grades that we could use, but it's not always that simple just to add them. We're always looking at new tests. Another thing I should mention is that we're always looking at new polymers and new modifiers. Again, I would say that it's important, in my opinion, to try some of the new options that are out there, but I also think it's important to get another point of view on those as well. So if someone's got a new way to do it, and they've tried it with a different firm or a different agency, those guys might give you some insight on what worked or didn't work well with them. CAP is also a very good resource for some of these questions as well. And then finally, be careful with specifications. I didn't really talk about it a lot, but as specifications change, people tend to drop some of the old specifications. They think they don't need them anymore because they have the new great specification. And that might be the right answer, but it also might completely change the binder that you're getting if you remove the specs. So it's important to try to understand the whole picture when you put a spec together. And then finally, you get what you specify, but you really get what you inspect and what you test. So hopefully people are still awake. There are a lot of things I brought up that I think we could spend more time on, but if anyone has questions, I'd really like to talk about whatever you guys want to hear more about. Thank you.
Thanks, Ryan. I haven't seen any questions pop in yet. So with that said, I have a couple of questions. When you're talking about the binders and the flexibility, I guess,
Yes,
of
elasticity.
the elasticity, but I'm talking more about flexibility than elasticity,
Okay.
but I guess kind of the same thing. Um, and one of the things that I have heard from years and from your predecessor was that overheating the material in the manufacturing process cooks the light ends out of the binder, which then takes away the flexibility, even though, the binder came through your lab and everything, and it's showing all the elasticity that it's supposed to have. But by cooking the light ends out, that flexibility or elasticity goes away. Is that true?
That is true. And you know what, Tom, thank you for bringing that up. I need to add a couple slides in here to mention that. It's hard to speak in absolutes because it really depends on the manufacturer where that exact temperature is. But to piggyback off of what you say before I would answer, I would say I've also seen that in the lab. Somebody's going to do a mixed design with a binder and they don't do it on purpose. And that 1 gallon, 1 quart container sits in the oven at 350 for 12 hours or overnight before it's used. You're going to get that same thing. So I'm trying to keep this presentation generic. I would say that for a hot mix supplier or a mix designer or an agency or engineering firm, if they're worried about it, I think you need to get your asphalt supplier involved in that conversation. And what will happen from a hot mix standpoint, since that's what you mentioned first, usually that seems to happen in the beginning of the season or the end of the season, or if somebody's changing to another grade or another binder, anytime that people are bringing binder in and then sitting on it for long periods of time, it might even be a rainstorm or something like that. So we always encourage our customers to minimize heat, which is easier said than done. Those hot mix plants aren't designed to, turn the heat off in an hour and turn the heat back on in 2 hours and then talk to the binder supplier. I've had experiences in other places where we've even worked with the hot mix manufacturer to take binder back so that it didn't age like that in the plant. So that's a good comment.
Yeah, my follow up to that is that, and you did mention spring and fall, or early season, late season, and people seem to think that is a problem solver. Well, we'll just turn the heat up and we'll instead of producing it at 310 or 300 or 290, whatever, well, we'll turn it up to 350, and they see that there's no issue with that, and they feel like there's no issue with that, and it's like, everything that I have been told, everything that I have ever read says that taking it outside of the binder manufacturer's guidelines, which, here Suncor, you're telling people, the optimum range to pump this through the plant is, and I'm throwing out numbers and nobody stick me to these, but 270 to 300. And when you get to 300, then you're kind of, I guess, voiding the warranty, for lack of a better way to say it. Is that really kind of the truth that, once you get to that point, you can come back and say, oh, your binder was crap, Ryan. And you go, well, what'd you heat it to? 340? Well, that's like taking a set of car tires and running them over razor blades at that point.
Yeah, again, I think that's an excellent point. I don't know if we would void the warranty, but what I would suggest to get around that is just a discussion ahead of time. Because the other element to this that Tom and I both talked about is time, right? So if you're, to use your example, if you're 270 to 300 and you're at 350 for, I don't know why you would do this, okay? But if you were at 350 for an hour, it's probably not a big deal, right? If you have that can of asphalt at 350 for 2 days, that's a big deal. So that's where we encourage people to talk to us. And if you're outside of that mixing and compaction range, we're saying that you're not going to get the performance that you would expect from that binder. Maybe
And that's really what I was talking about, not necessarily the storage temperature of the liquid, but
right.
the manufacturing temperature in the drum, because that's where they turn the heat up. They don't turn the heat up at the storage on your liquid. They're turning the heat up when they're burning or baking it in the oven. And that's where and tell me if this is not true, but in the storage container, the tank, the light ends are moving. They're staying pretty much in the tank and they're moving through the circulation process. But once they go into that manufacturing drum, then they're allowed to burn and fly out of the drum. I don't know a better way to put it, exhaust out of the drum because you've burned off the light ends. But I've never in 40 plus years heard of anybody turning the temperature up on the storage of the liquid. They always burn it when they're running it through the drum. Have you heard anything different?
Well, yeah, but not in Colorado. The thicker the binder is, just in general, and I'm not even talking Colorado specific here, but the more people have to heat it, I don't think it would be as big of an issue here. But the other way I would say what you just did, and I agree with you completely, is when you're heating up something in a tank, hopefully it's being circulated, but even if it's not, that tank's moving around over the coils. You're probably not getting a whole lot of localized heating. When you put that binder and everything really in the drum, it's like taking that hair dryer, turning on all the way and focusing right on one spot on your head, right? You're getting as much as the maximum effect you can from that temperature on a localized spot, and it's going to age a lot differently and worse than if you're just heating it in a tank. So I agree with you completely. That's a good point.
Yeah, that's always been my response to that is that um, we have people not understanding through the manufacturing process. They have people in the field are going, well, it's going to be a 35-degree day, but we got to pave, so just turn the heat up. It'll be okay. That's
Yeah.
like, okay, it'll be okay for today, but in 6 months you're going to be pissed off when that stuff starts cracking because it got so brittle. You aged it during the manufacturing process, and then it comes back to not a warranty back to the binder supplier, but it comes back to a warranty from the producer, or not, or even just the contractor, because the contractor's buying it and it is not the producer. And it's people are putting themselves into a situation that they probably don't want to be in. Um, and I know you hear this all the time, Brian. You and I have talked about this a number of times, but
Yes.
so here's where I would say, this is what I would say, and I want your comment on this. So if you have this situation early spring and late fall, in 2021, we have a solution for that. And it's leave the temperature where it's at, or even drop it 10 degrees and drop something else in to keep the material workable at a lower temperature. And I'm going to give you just a second to, talk just a minute or two on that process.
Yeah, I was going to go there. I'm glad you said something. Warm mix additives, and I would bet everybody who touches our industry at some point has heard about these. There are a variety of different options. Again, they're supplier specific. I don't think anybody has more than one option at a specific facility, but we have, speaking for Suncor, chemicals that we can add to the asphalt binder, and the entire point of it is to use your example earlier. In fact, there's a lot of uses. This would be another good presentation, but if it's 35 degrees out, to quote your example, instead of going to 350, you could keep it at 300, put this material in there, and it would behave more like it would if it was at 350. The material doesn't cool down as much. You end up with better compaction at cooler temperatures. There's a lot of benefits to that product. So there's a good solution that doesn't do anything negative to the binder, that you can still get the performance you're looking for in cold weather. And I believe this is secondhand, but well, the coldest I've seen, maybe is the way to say it, but I was on a project again in another state where we were in the low to mid 30s, and it was a 3-hour haul time for the hot mix, and they still got compaction with it. So there's some good options that are out there.
My best example that I can give you, Ryan, personally is I saw a project that was going down it was about 25 degrees and snowing, and they had no issues getting the material down in place and compacted. And that was 5, 6 years ago, and it's still sitting, working, functioning as well as it was that day. So that's my example that I personally can see, and I've heard, the same ones that you've heard. We run in the same circles, right?
That's right.
So the other thing that you're talking about, the WMAs, and from my screen, we call it workability mix additive. You called it warm mix additive.
Okay.
That's all a nomenclature thing and the reason that we in our office call it workability mix is because I convinced everybody in our office that warm 270 degrees is not warm. It's still pretty damn hot. So, and people are dropping it in at 300, not dropping the temperatures at all during the manufacturing process just to make it more workable. So that's where we've kind of landed with WMA, not to get rid of the acronym, but to just, make it so it's more a reasonable definition. Hey, it makes it more workable at 300, at 270, at 290. And I've seen here recently, we're starting to see more and more of it dropped into polymers, into polymer modified binders, just because it makes them more workable, especially the SMAs where they're tough anyway. So you guys, I know you've seen it because you're supplying it, but that's one of the things that we're looking at. Well, I kind of stalled to see if there'd be any more questions. Go ahead, Ryan.
There's a lot of different uses for those products. You don't have to reduce your temperature, and you can use long haul. I haven't been on a project like this, but 3, 4, 5-hour hauls and still not had issues. I think the most I've seen is 3 hours personally. But there's all kinds of different aspects to those products that you can get out of them. They're definitely good options out there.
Well, one of the people on the call today is from down in the Buena Vista area, and I know that they have some pretty long hauls out of there, but it's not necessarily their own trucks that are hauling it, but they're having people go in there and they're hauling long distances, and so it would be a real benefit to them. And we can't talk anything about money here, but I can talk about cost and the cost benefit ratio. The cost is minimal compared to the benefit is what I guess I would say from my perspective, is that it's a minimal cost during the production. It's a major benefit on the back end. And actually, I was talking to a producer here in the Denver area yesterday that told me the cost is inconsequential to them because they spend anywhere from 10 to 25% less time during the placement compaction phase. They can get done faster, so they're in and out faster. So anyway, we can't really talk about cost. We're not talking with money here.
I would just say, and it's not going to be specific about cost and whether it's workability mix additive or recycled materials that are new on the scene or anything like that. I think in some cases it's worth figuring it out for yourself, because people can tell you whatever they think. Try it out and see what you see.
I agree totally. All right. Well, I did get something here. Hang on. Yeah. got a comment.
Got a comment.
Got a comment. Yeah. So Eli, thank you, Eli. They're using WMA toward the end of their last season down there in the Buena Vista area. So that's great. You know, to me, I mean, if I'm Fred, the producer, Ryan, I'm calling up you or John or somebody over there and saying, send me out, you know, how many tons I need. And every ton would have the WMA in it. There would be no question in my mind, but hey, you know, it's a new technology. It's only been in the United States since 2003.
Time flies.
All right. All right. Well, haven't seen any more questions, Ryan. This was great. The information and then just our last 10 minutes worth of conversation, I think were worth the whole time of everything we put in, at least for me. So I want to thank you, Ryan, for giving us your time and effort. Thanks, Suncor Energy, for allowing you to do this to it for us. Thank everybody for being on today. I'm going to switch back to
one more thing, Tom. My phone number's up there. If anybody has questions, I'm more than happy to take them outside of this presentation. And thank everybody for coming, and thank you, Tom, for hosting.
Yeah, I want to tell everybody too that's on or that will be listening to this at some time in the future. Ryan is a great source. One of his coworkers, John Wilkins, if anybody's interested, I can hook you up with either one of them. They're great sources. You have any questions about binders, anything that's going on, I mean, I can hook you up. So I want to thank all our sponsors again for helping us to put these webinars on. And we hope to see everybody again soon, and everybody stay safe and healthy out there. Appreciate everybody being on.